By using recursion within transformer models, you can build a model that performs almost as well, but allows you to have fewer parameters, which means less VRAM, and potentially allows you to do dynamic compute without having a long series of thinking tokens. This is a concept that has been explored in smaller models. It's been explored in the ARC Prize, in the TRM paper. It's also been explored at the Llama size paper with the Hugin type models, but it has not really been scaled to full size. There's also limited comparison between typical transformers without recursion and then recursion versions. So I thought it would be interesting to take a well-known architecture and approach, Nanochat from Karpathy, which is a small 20-layer model, and replace 12 of those layers with 4 recursive layers and see if I train it for the same number of flops, whether I get the same, better or worse performance. So that's what I've done, and I'm going to show you this model that I've made public. I'm going to show you the repo. I'll go through some of the changes I've made there, and I'll go through some of the theory about what recursive models might offer as a meaningful improvement to how transformers are designed today. I'm curious whether the large language labs are already using aspects of recursion because I can see some strong benefits. There are also some complexities around things like doing torch.compile for training and also running continuous batching during inference that I'll talk a little bit about. Now, for background, this is all based on the Karpathy Nanochat repo, which you can find on GitHub. It allows you to train a model for about $100 that can respond pretty well to you in English. It's able to score, roughly in the vicinity of GPT-2. The model is quite small. It's about a 500 million parameter model. And the comparative model I will train is 300 million parameters, so a bit more than half the size. I trained and I made a video previously on Nanochat. And if you like, you can find a copy of that. I'll show you here. Just go to Hugging Face, Trelis, and Nanochat, and you'll find all of the files. And you'll also find my fork of Karpathy's GitHub repo, which explains how to train and spin it up quickly using RunPod. To advance on that, I took the very same model. I trained on the same amount of data and using the same number of flops, but instead of having 20 layers, I took out 12 of the middle layers and replaced them with just 4 layers. Yeah, I said 12 earlier, but it's 16 because I have 2 prelude layers. I have 4 layers in the middle that are recursed, and during training, I will recurse them for an average of 4 times. So 2 plus 4 times 4 is 16, plus 2 is 20. So I have the same number of effective layers with the mean recursion, and I'll talk about exactly how the number of recursions is decided during training and during inference. And I completed the exact same pipeline, the same pre-training, the same mid-training, and the same post-training as the original Nanochat model. And here are the results. So you can see this chat core metric, which is a mixture of some of the following metrics: ArcEasy, ArcChallenge, MMLU, GSM8K, Human Eval, Spelling Bee. And the core metric here, if you look at the original model, scores about 0.27, whereas the recursive model scores a little bit lower than that. So when you train for the same number of flops and data, you basically get quite similar performance. And you can see as you vary at inference time, the number of recursions on those middle 4 layers, you get, maybe a small increase here. Now, I'm not showing error bars because I didn't rerun this experiment. It costs about 100 every time you want to run it. So you can say that probably the difference here is not all that large, and the trend here is probably also not all that large to be statistically significant. But what is meaningful is that you were able to get a model that is close to half the size and is able to perform quite similarly here in performance. It's particularly interesting if you look at metrics, benchmarks around more reasoning type capabilities like GSM8K, which is grade school maths. This benchmark involves maths problems, and here you see a very big improvement, at least going from 2 to 4 recurrences around the middle layers in the performance. This is definitely meaningful. We've got 3.5 going all the way up to, well, very likely meaningful, up to about 6% performance by going from 2 up to the mean training number of recurrences here. Now, again, I'd need to run this a few times to ensure that this is statistically significant. And with this kind of a small experiment and model, I'm not sure I would draw too much conclusion from it. But suffice to say, I think there's evidence that training a model with recurrences on an isoflops basis can lead you to get a very similar performing model with recursion but a model that is smaller in terms of VRAM and potentially allows you to do adaptive compute. Something I'll talk about more here. I won't prove that adaptive compute is able to work well from a commercial mindset. That would require more. I would need to show you probably more difficult benchmarks. Also would potentially need to train for longer. My performance right now in reasoning benchmarks here is not that high, and we didn't do any reinforcement learning or anything like that, although Karpathy's repo does support that, so it's something that could be interesting to do as a further step. What I'm going to do now is go through some of the theory here. I'm going to show you on my iPad. I'm going to sketch out a few things, and when we're done with that, I will go into the repo and I'll show you some of the lines of code that I changed in order to get this recursive model to work. All right, let's go through some of the theory. I want to start off and talk about the motivation. So why would you even want to do recursion? And the short answer is that it allows you to have a smaller model and potentially do adaptive compute, which ultimately could save computed inference time and get better performance. Then I want to talk about the architecture. I don't think that's correct. Architecture. And then I want to talk about training. And I'll maybe talk a bit about inference and adaptive compute. All right. So motivation. Let's write it here. 2 reasons why you might want to do recursive models, at least. The first one is, let me write that in black. Smaller weights, so a smaller parameter count. And what this means is you can probably fit more easily on, say, an iPhone or on a Mac, a laptop. It also means you can fit on fewer GPUs if you're doing training at scale. If previously you needed to split a 20-layer model across 2 GPUs with 10 layers on each, you could now maybe fit it on 1 GPU. If you've less pipeline parallel, that's called pipeline parallel, well, you put them in series or model parallel, then you have fewer pipeline bubble issues. This is, it's kind of a technical thing during at-scale training, which I don't do a whole lot of. But if you have GPUs in parallel, what you end up with is GPUs waiting on previous GPUs, and this leads to a bubble that propagates through the pipeline. And that is going to affect the utilization of your GPUs and ultimately increase the training time. So a benefit of having a recursive model is you can fit it on fewer GPUs. The second benefit is it opens up a pathway to adaptive compute. And the idea here is, instead of doing a reasoning model where you generate more and more tokens, you instead just do more recursions on the model, and you increase the number of recursions if you want to have more reasoning. And this is appealing because you're doing recursion in latent space. If you are generating more tokens, a token is actually just one sample from a probability distribution. And that means when you take that sample, you're actually throwing out information. But if you stay and do the recursions in latent space where you use the full information, that's potentially going to be a richer way to do recursion. And also, it allows you to break the link between needing to generate a token to do reasoning. Even if that token is very easy to predict, you still take the same amount of compute in a reasoning model. Whereas if you can increase the number of recursions, there's no tokens being generated. So you break the link, which is constraining between token generation and doing more compute. It's kind of a subtle point I might explain on another video at some point. So these are the 2 reasons. If you don't understand adaptive compute yet, we will get to it when we move to the inference section, so don't worry too much. All right, so let's talk about architecture and do that by starting with the standard transformer. So in a transformer, I'll draw out what this looks like. You will start off with some inputs. So down here, you will have some text input. And that text will be broken into subwords or tokens. And those tokens are going to go through an embedding layer. So here we will typically have an embedding layer. And the embedding layer is a lookup table that will take each token, maybe out of a vocabulary of 65,000. And for each token, it will convert that token into a vector in high dimensional space. So we have now got embeddings or vectors. And then these will go through the transformer layers. And here I'm just going to draw 3 transformer layers. The vectors will propagate through that. They'll be transformed. And when they come out the other side, I need to make space here, they will go through basically reverse embeddings. This is often called the LM head or the language model head. And the language model head takes vectors and it converts them into a probability distribution over possible next tokens. So it might say the word the is 20%, quick is 30%, and brown is 40% or 50%. And you will then sample typically the most likely token in order to continue your sequence. So here you have token predictions. Token predictions. That's a typical transformer. And let's write down here, typical. Now, what if we want to do recursive? In this case, we're going to do a lot the same. We're going to keep the embeddings layer. But we're now only going to put in a smaller number of intermediate layers. And I should say that each of these layers here consists of attention, which allows tokens to take information from previous tokens, and also multi-layer perceptrons or feed-forward layers. These take a vector representation of a token, or a vector representation, I should just say. Let's say 256 dimensions, and it allows each dimension to pay attention to the other dimensions. So that's the feed-forward layer. And then the attention allows all of that to pay attention to take information from the previous tokens in the sequence. In the recursive transformer, instead of having, say, 3 layers here, we will just have 1 layer. And rather than just passing through it once, we will actually recurse like this. And then we will have the LM head. So when I took Nanochat, and Nanochat, I should say, has got, let's talk about Nanochat. I'll make this one here blue. If I look at Nanochat, it will have 20 layers, so 20. And in the recursive case, I actually keep the first 2 layers, that's called prelude. Then I put in 4 layers here, which are my recursion layers, and then I keep 2 of the last layers. Now I'm pre-training from scratch, so when I say keep, I just mean keep from the base architecture. So in the recursive case, I only have 8 layers compared to 20, but this middle one here, I will recurse a mean number of 4 times. So my number of recursions on average will be equal to 4. So actually, I've got an effective number of layers of 2 times 4 times 4. And it's actually not 2 times, it's 2 plus 2 equals 20. And so that's how I've got 20 effective layers in the recursive and 20 in the original model here. So that's the recursive model. Now there's a little nuance here around how do you add information back. One way you could add information back is just simply by adding the output back to the new inputs. So if you think of it as the new input, so let's call it the mixed input. So if I say that what's coming in here is the mixed input, if I say what's coming in here is I, and I say here is the recursion, a simple way to do this is you can just say M is equal to I plus OR, and you can just add on a vector basis. So if you have I1, I2, I3, and then you have OR1, OR2, OR3, you could just add them to generate a new vector that would be M1, M2, M3. And that probably would have worked, but in literature you'll find another approach, which is allowing for a little bit more control. Basically, if I do this, The model has no way to weight the I versus the recurrent stream. It's just adding them. But if you want to weight the recurrent stream, what you can do is you can instead concatenate. So you concatenate such that you have I1, I2, I3, and then you make the vector longer by doing or1, or2, or3. And now you have a vector that's twice the width that it needs to be. So you put it through an adapter layer. You put it through a simple linear layer. This is just your adapter. And you adapt it down to half the size to make M1, M2, M3. So this is actually what I do. I concatenate the vectors and then I use an adapter, which is trainable. So this is trainable. It's a simple linear layer. So you can think of it just matrices that map down to a smaller dimension. And yeah, this is how I do the mapping for each recurrence. Now on the very first recurrence, these values of OR are just 0. And you start off from that. But on the later recurrences, these values will be non-zero as you start to build up information in the recurrence. There's another subtle thing here around inference. If you want to boost or if you want to give a kickstart on a given token, instead of starting these ORs at 0 on the first recurrence, you can use the OR values that you had from the previous token. You can use the last recurrence OR values from the previous token to give a kickstart. Kind of a subtle point, but allows you to get some boost in inference. And I am doing that in the code for what it's worth. Okay, next I want to talk a bit about what do I want to talk about? That's the architecture, the training. Okay, so what I described is kind of all you need to know to make the model recursive. You could run Karpathy's Nanochat without changing much. I did something a little more complicated, which is I'm actually training using different levels of recursion. So the model gets used to seeing different levels of recursion and hopefully can perform better if I lower recursions or raise it during inference. So instead of just using 4 recurrences, if I draw, I'm sampling the recurrences. So I've got here on the x-axis, I've got my number of recurrences. And this is during training. And I'm actually doing a Poisson log normal. So if you look at the probability here on the y-axis, I'm setting this up so that the mean value is equal to 4, which allows me to keep constant the number of layers that I'm doing compared to the original. And I'm also capping here. I'm capping at a value of 16, the maximum level of recurrences, and the minimum here is 1. You could maybe do 0, but that would be a discontinuous jump for the model. So the minimum number of recurrences is 1 and the maximum is 16. And this allows the model to sometimes see more recurrences, which hopefully can allow me to better leverage that if I want to do adaptive compute at inference time. Now, there's one issue here with training, which is that if you train with a constant number of recurrences, there will always be the same pattern of calculations as you run a forward pass through the model. But if you vary the number of recurrences, there are actually different paths. And this is important because torch.compile, it caches or remembers a given computational path, so it can replay it much faster in later training loops. It often saves you about 30%. But now that we have 16 possible paths, because you can either go through with 1 recurrence, with 2, etc., up to 16. We've got 16 paths that you need to cache, and this slows down training quite a bit during the first hour. This wouldn't be a big deal if I was training on a lot more data because everything would be compiled, the graphs would be compiled, and that would end up a small portion of total training time. But because this is not a very long training, it's only 4 hours, it ends up slowing down training from 3 hours to, I don't know, close to double that when I do the recurrent model. And you'll see that in the weights and biases curves I show you. So this pre-training, which maybe was overkill for a first model, I should have just kept it constant at 4, but it does allow you to then probably better vary the number of recurrences. You probably could vary the recurrences anyway, even if you only trained it on 4. This has been tried on the TRM model for Sudoku, and it actually works, just increasing the number of recurrences at inference time. It doesn't work on ARC AGI2, although that's harder. And I suspect if you pre-train by varying recurrences, it probably does help. And I think that's what's being borne out when training Llama or Qwen type models. So this that's my comment on training. Now for inference, I just want to talk a little bit about adaptive compute, which is kind of a subtle concept, and it's got some implications for whether inference would work well or not. But if you look at adaptive compute, the idea is, well, the simplest idea is if you have a hard problem, you would do more recursions, maybe 16. If you have an easy one, do 2. The question is, how do you know in advance how many recursions you should do? And one approach to it is you could train a halting head, as the TRM paper does. So you could actually add on an extra head here that kind of taps from the recurrent layers and put on a halting head that would predict when the solution or high quality has been reached. This is kind of hard to do though, because if you're working with language, it's not obvious what a good quality answer is necessarily. So it can be hard to train a halting head. And a simpler proposal, and I'll link the papers in the description, and I should thank Sean McLeish, by the way, for discussions around some of these topics. But a simple approach is just to look at, as you run recursions, look at the probability distribution of tokens predicted. So let's say the possible tokens are there, quick and brown. If you're on a first layer, so let's say recurrence equals 1, you maybe have this kind of a distribution, and these all need to add to 100%. If you have or equals 2, so after your second recurrence, maybe you have something like this. And then maybe after your third recurrence, you have something like this. Let's say you've now got this. So notice how on that third recurrence, my probability predictions, my distribution is very similar to the second one. Well, you could just determine a rule whereby when my probability distribution looks similar after 2 subsequent recurrences, that means I can probably stop. Mathematically, you could look at the KL divergence across the full probability, the full softmax. And if the 2 distributions are very similar, then you say, okay, we'll stop recurring now. So this is a simple rule to decide when you should stop recurring. Now, there's a little bit of complexity because when you stop recurring on a given token, you may find that different tokens have got different optimal amounts of recurrence. And what this leads to, I'll just show kind of somewhat graphically, although not rigorously. If we look again at the quick and brown, remember that when we do attention, we look back and grab information from earlier tokens. But now the number of recurrences might be different. So we might have some calculations done for the word the for recurrences 1, 2, and 3. But for the word the optimal might be just 2. And for brown, it might be, again, 3. And so when we get to brown, typically when we're here, we would expect to be looking back at information from the same layer. But this is missing because we've only done 2 recurrences. So whereas in a physical network with 3 layers, we would always have this value available, in a recurrent network where we stop after 2 recurrences for quick, we basically have missing information. The solution to this is you just take the latest available state. So that pretty much solves it. And actually, whereas in a dense network, you typically would store the KV cache for each of the layers. In a recurrent network, you could decide to just throw away the history. So if you recur 3 times, don't bother storing for the first 2, just always rely on the latest. So you can basically throw out some information from the past and only rely on the latest information. And this allows you to reduce your KV cache, and it seems empirically this allows you to keep good performance as well. So you can probably achieve inference in just as simple a way when you're running with adaptive compute, well, when you're running with a recurrent model as with a standard model, except there is an important subtlety here, which is that if you recur to different depths at different tokens, when you try to do continuous batching with multiple sequences, so this will work straightforwardly with 1 sequence, but with multiple sequences, you typically, in an inference engine like vLLM, you will pack together the next token prediction for multiple sequences. And if those different sequences will have different levels of recurrence, they're going to finish forward passing through this network at different points in time. And this poses a problem because you can kind of keep forward passing, but then you will have to wait and you will have to idle any of the sequences that have finished recurring while you run the other ones. And this is suboptimal because you won't be using your CUDA cores to the same extent as you would have. And basically all of them, it's kind of like you'll be using whichever the max in that sequence needs for recurrence. So if you've one sequence that needs recurrence of 16, but the others only need recurrence of 2, well, the ones that only need 2 will kind of be idling until you get to 16. And so you need to think about, well, can you improve upon that? And probably you can, but your engine will need to change because you'll need now to somehow split up the portions of what's happening in the LM head. You'll need to split up some kind of engine logic for your recurrent block and then some engine logic for the embeds. There's maybe an analogy to how you split up prefill and decode, but now within decode, you need to split up these different parts. I'm only touching here on the ideas involved. It'll just give you a sense if you're familiar with Inference. But you would need to think about this in a lot more detail if you want adaptive compute to actually work well with continuous batching. Okay, what else have we got? Training, architecture. I think that's what I want to explain for now. I'm going to show you the weights and biases training logs, and then I'll show you some of the code. You can find the weights and biases logs if you just go to the Hugging Face repo, which is in the Trelis research org. And I've got a recording here of the original D20 model. That means depth 20 when I trained the Karpathy model. And you can find my video on the Trelis research org on YouTube, or rather Trelis research on YouTube. And let's go through a few of the things here. So first thing I want to show you is the training and how I've run this twice. I've run the recursive model twice. And yeah, basically the first time I ran it, it stored the KV cache. So the second run was faster for that reason. But what you can see here is if you look at the training, the tokens per second, you can see the tokens per second is quite bumpy for the pink curve, the magenta curve. And that's just because you are doing this KV caching and you're trying to store the KV cache for all of the 16 permutations. So it slows down the inference rate a lot. And you can see that on the mean flops utilization. It's quite a bit lower here than blue at the start, but then it starts to trend up. And you end up reaching a training speed that's probably about 75 to 80% what you get in the case of the dense transformer, the full 20-layer transformer. And you can see if you look and turn on the green one, you get somewhat of a similar asymptoted speed, but there is a little less of a slowdown at the start because some of those configurations have been cached already. Now, if you look at the total training time, you can see here that in the case of the magenta one, where I'm caching all of those graphs for torch.compile, it's really slow at the start. So you can see it's taking up a ton of time, and then it starts to proceed at a rate that's close to the original run. And because I've pre-cached when I reran the recursive case, it doesn't have that initial slowdown, but you can see the slope of that graph is a little bit higher, so it is slower. And that reflects that the mean flops utilization, or the tokens per second, is a little bit lower as per these curves here. Now, if you look at the training loss, it's very similar in the original model and in the recursive model. If you look at the validation loss, it's also fairly similar. It's a little bit higher in the case of the recursive model than in the 20-layer model. The grad norm, interestingly, the grad norm is quite a bit higher. It's still pretty stable though. There was a spike there on the orange or on the magenta curve, but pretty stable down below 0.5. So I don't really see any issues with training at the same learning rate as I had used in the case of the 20-layer model. Just for your own knowledge, by the way, when I ran my first recursive model, I ended up training it on a little bit too much data. And yeah, it's just because I did a miscalculation. Basically in the code, if you're going to do recursions, the way Karpathy has things set up is that the amount of data that it gets trained on is what's called chinchilla optimal. So it's trying to be compute optimal, at least on a training basis. And that means using 20 tokens for every parameter. But if you now have a reduced number of parameters only because of recursion, you really need to think about effective parameters, not actual parameters when you, well, this is probably an open question. It's not obvious what chinchilla optimal would be for a recursive model. But what I knew is I wanted to keep the data constant and I wanted to keep the flops constant. So I had to adapt to use 34 tokens per parameter instead of 20, because my model is roughly, it's roughly 20 over 34 times the size of the original model in terms of parameters. And I wanted to keep the amount of training flops constant. So I got that calculation wrong in the magenta case, but I got it right on the second time I ran. And that's why you can see the curve here for the loss, for the learning rate schedule. Basically, it's a constant learning rate, and then there's some linear annealing towards the end here. And if you look at some of the benchmarks, so we've got, sorry, it's a bit cold here. If you look at the benchmarks, you can see the core metric kind of improves roughly in tandem. And the other metrics here, I mean, they all look kind of similar within noise. Probably the recursive model is a little bit lower. And all of these, by the way, are calculated with a level of 4 recursions. But yeah, you can see they all probably look fairly similar. What else do I want to show? I think that's pretty much it on the data side. You can take a look yourself if you want. I'll go back now and I'll take a look at the repo. I've cloned the repo here and I'm in the recursive branch, by the way. And let me see if I can show some of the changes. It might be handy to take a look at the changelog, because that will explain more clearly some of the changes I made. So here, when I add support for recursion, there are some changes. I'm looking here at the base training setting. I'm setting the number of prelude layers to 2. The recursion block is 4. The coda block is 4. The mean number of recursions is 4. So I've got an effective amount of 20. The max is 16 recursions. And yeah, this is important as well. I didn't mention this, but actually when I backpropagate, I will backpropagate through a maximum of 4 recursions. This means backpropping through all of the recursions if I'm using 4 or less. But if I use more than 4 recursions, I don't backprop through all of them. I only backprop through the last 4 of them. So if I have 16, I only backprop through recursions 13 through 16. And it would be more accurate to backprop through all of them, but it would also take a lot more memory. And so it's common to just take this shortcut, which is not, it's not theoretically exact, but seems to kind of work. There's probably still debate around the degree to which you should or shouldn't do this. And yeah, you can see the model configuration is updated. Instead of just being simple here, you need to include parameterization for the number of prelude, coda, and recursive blocks. This here is how I'm sampling. So I'm taking, this is my Poisson log normal with a sigma of 0.5. And yeah, what else should I explain? When I run the eval, I need to specify the number of recurrences. There's nothing too complicated there. And then I do allow for running eval with multiple values of recursion. So I will run it at 2, 4, 8, 16. That's what gives me the plots I showed at the start of the video. I'm not doing dynamic compute, so I'm not dynamically trying to do recursion on a per token basis. That would require some more logic. So that's one of the key things. As I mentioned in the theory section, you need to properly initialize the recursive part, because on the first recursion, that recursion should be just zeros. Or in inference, you can kind of preload it with information from the previous token. And that's where I think I made a small update here. Yeah. Actually, on the very first one, you need to initialize the adapter correctly. So I can't easily show my iPad, but the adapter is what takes in that vector that's twice the length, because it's got both the input and the recursive piece, and it shrinks them down to the same size as what the input needs to be when it goes into the transformer layer. On the very first go around, that adapter needs to ensure that it passes through only the input and exactly the input. So it needs to like be an identity to map, to mirror through the input while zeroing what the recursive component is. If you don't do that and you just have random adapter values, the input won't get passed through neatly, and it will lead to bad convergence, at least bad kickoff of the model's value. So initially I set the adapter to be identity to pass through that input cleanly, and then over time the adapter will migrate away from that. What else? Yes, so torch.compile, it now needs to be dynamic. Typically this would be false because the graph is constant if you've 20 layers, but you need to make it dynamic, which does slow down, and that's probably partly why we reach mean flop utilization and token throughput that's a bit lower than what the 20-layer model is. Also, there's just variance in the training because when you train now, although each batch will have the same number of recurrences, yeah, you just have fluctuations from batch to batch with different recurrences, and that's going to hurt probably your mean token throughput. What else? I've added saving so that the model is saved periodically so I can recover. And I think that's mostly, yeah. If you turn off, you can also turn off torch.compile and just take that slowdown and then save the time needed to compile. This makes sense actually for mid-training because mid-training is really short in Nanochat. And if you do want to keep on torch.compile, it's going to take forever to train because you're going to spend most of your time compiling the caches and then not really use them because the training is so short. So you can turn off torch.compile. If you turn off torch.compile, you will use more memory, so you need to reduce your batch size. So I had to reduce the batch size for mid-training. Now, arguably during mid-training, you should just do it with a constant level of recursions, which would have been the simpler fix. But yeah, I decided to also keep that Poisson log normal for both mid-training and for SFT as well. So that's a quick overview of how that works. And that rounds out the video here. I'm excited about recursive models. I don't think it's a slam dunk. It's not like I'm getting a really big free lunch or even any free lunch necessarily here. But the fact that it allows you to make smaller parameter models, and the fact that I see potential for the adaptive compute to improve performance is exciting. It strikes me as more intuitive to be doing recursions as a way to think harder than to be generating more tokens. So that has an appeal as well. And I'm looking forward to doing more research on this here. You can always check out what positions are open at Trelis if you're interested by going to Trelis.com or just reaching out to me by DM on X or else by email. If you have any questions on this, let me know down in the comments, folks. It's been a pleasure. Take care.